We're ready to learn Faraday's law in this lecture after we learned what is magnetic flux. Faraday found out that the EMF induced in a circuit is related to the change of magnetic flux. To be more specific, the induced EMF would be proportional to the rate of change of magnetic flux through the coil. So it's delta phi B over delta T per loop of wire. So if there are n loops of wire, EMF would be proportional to n delta phi B over delta T. We will discuss the negative sign later. Based on Faraday's law, phi B equals BA cosine theta. So we have a number of ways to induce EMF in a circuit. As long as the magnetic flux changes, we'll have induced EMF. So we can change magnitude of B, we can change the area of the loop, we can change the angle between magnetic field and the surface, or any combination of the above can give us induced EMF.
This is a demonstration of Faraday's law of induction. I hope you remember this demonstration because it's a very important one in the history of physics. What it demonstrates is that a changing magnetic flux through a coil of wire produces an EMF, namely a voltage, in that coil of wire and a current in the coil of wire. This is not something that people come across every day, but it's the basic principle behind generators, the alternator in your car, etc. So we can generate electricity by changing the magnetic flux, the amount of magnetic field that penetrates a coil. So what I have here are three separate coils of wire, one with very few windings, one with about double the number of windings, and one with approximately quadruple the original number of windings of wire in this coil. I also have and this is a galvanometer. It just measures the amount of current in the wire, in the coil. I also have a magnet, North Pole and South Pole. I'm going to be inserting the magnet into each of these three coils of wire, and we'll be watching the black needle here in order to demonstrate the presence of a current in these wire loops. So starting with the small one, if I move the magnet into the wire loop, you saw that as the magnet was moving into the wire loop, the needle bumped up positive. But now the needle isn't moving at all. And this is a very important bit of Faraday's law. There's only a current when there's a change in the magnetic flux. It doesn't care how much magnetic flux there is through the coil. Right now there's a lot. All that magnetic field is through the loop. What matters is when it's changing. So now I'm going to pull the magnet out of the coil. And what you see is that while the magnet was leaving the coil of wire, the current was negative. So we get an opposite effect. And we'll talk a lot more about that. The effect is proportional to the number of windings in the loop of wire. So we should see a bigger effect through this loop and finally for the third loop. So we definitely saw a bigger current, went all the way to the maximum and minimum, and then I think we actually pegged out here. It went beyond the maximum this galvanometer will measure. But again, a changing magnetic flux in a loop of wire causes a current in the wire, and that's Faraday's law of induction.
Electric guitar would be a perfect example of application of Faraday's law.
Electric guitars. Few instruments have had such an impact on modern music since their invention in the early 1930s. In fact, there's probably one playing in your favorite song. But when you plug a guitar into an amp, what's actually happening? The magic is in the guitar's pickups, which change the kinetic energy of the guitar strings vibrating into electric energy with the same principle that explains how electricity is made with wind turbines, called Faraday's law of induction. This is a sort of complicated law of electromagnetism, but for our purpose, just know that it explains how magnetic fields can generate electricity in the right circumstances, usually by moving them inside or through a coil of copper wire. You see, underneath each of the guitar's strings is a cylindrical magnetic pole, and these are coiled together with a very thin copper wire. Together, these create a small inductive sensor, which is a device created by applying Faraday's law that will generate an electric current when the magnetic field going through it changes. This is important because guitar strings are always made out of nickel or other metal alloys that are magnetic, so when they are strung over the magnetic poles in the pickups, they generate their own magnetic field, and when they vibrate, their magnetic fields also vibrate through the inductive sensor, which by Faraday's law creates an electric current. This current is sent through a cord and into an amp where it's converted back into the sound of a guitar string being plucked, or just as often, distorted into something totally different.